Another place where L'Hopital's rule comes in handy is when you need to compare the growth rates of two different functions. For example, let's suppose that you're a medical researcher working in the lab, experimenting with different medications on cancer tumors. You might want to compare the growth rates of two different tumors as they behave under different medications. How do those growth rates relate to each other? Here's the rule. Suppose that the limit as x approaches infinity of f of x equals infinity and the limit as x approaches infinity of g of x equals infinity. So we're looking at two functions with infinite limits. That is, these two functions are growing without bounds. But the question is, which one is growing faster? Now, please correct my typo on your notes here. It should say, then f grows slower than g if the limit as x approaches infinity of the ratio of these two functions, f of x divided by g of x, is equal to 0. So if g is growing faster, right, they're both approaching infinity, we have L'Hopital's indeterminate form, infinity over infinity. But if g is growing faster, that means the denominator is growing faster than the numerator. Therefore, the value of the limit would be equal to 0. We could also flip that around and say f grows faster than g if the limit of this ratio is infinity. So if you learn the logic there, you learn to understand those limits, then you won't even have to memorize this rule. Now here's where it gets interesting. If the limit as x approaches infinity of the ratio of f divided by g is m, where m is a positive number and it's finite, then f and g have comparable growth rates, and that limit m is going to tell us how those growth rates relate to each other. In example 3, we want to analyze the relative growth rates of the two given functions. Example A, natural log of x to the 20th and natural log of x. Notice both of those functions have a limit at infinity that equals infinity. That is, both of those functions grow without bounds on the far right side of their graph. But we want to know who grows faster. I don't know about y'all, but my bet is on this first one. But let's prove it. Let's be specific. So let's find the limit as x approaches infinity of the ratio of these two functions. Now, if you learn how to interpret this limit, you can put those in any order. Natural log of x to the 20th on top or on the bottom. Now, we have the form infinity over infinity, and of course that gives us the green light for L'Hopital's rule. So we'll individually differentiate the numerator and the denominator. So in the numerator, I'm going to put the argument in the denominator and the derivative of that argument in the numerator. And in the denominator, we're going to find the derivative of natural log of x, which is 1 over x. Now, let's do some algebra to cure this complex fraction here. We're going to multiply both the top and the bottom by x. So that's going to clear the denominator. And we can simplify this to the limit as x approaches infinity of 20. And notice if we multiply these numerators, we'd have x to the 20th over x to the 20th, where, of course, those x to the 20ths cancel. So now we're looking at the limit of a constant. The limit of a constant is a constant. Thus, the value of this limit is 20. Now, since natural log of x to the 20th was on top, we can say that natural log of x to the 20th grows 20 times faster than natural log of x. And doesn't that make perfect sense? If I take this exponent and apply log properties and move that down as a coefficient, I can clearly see that the first function is 20 times the second function. Now, you may have seen that all along. You may have thought to apply that right here. And if you had moved this exponent and calculated the limit without doing all of these calisthenics, you would have still ended up with a limit of 20. So if you thought that, great job. Now, here's a good question. Who grows faster, 100 raised to the x power or x to the x power? Well, let's find out by taking the limit at infinity. So the limit as x approaches infinity of 100 to the x divided by x to the x. Well, notice our indeterminate form here is still infinity over infinity. Now, if I want to apply L'Hopital's rule directly, that means I'm going to need to differentiate x to the x power. We have done that in a previous video in our notes, but you may not have memorized it. So if you don't have it memorized, what are you going to do? Well, here's another option. Let's rewrite this as the limit as x approaches infinity of 100 divided by x raised to the x power, because they both share that common exponent. Then let's go ahead and introduce a left side. Let L equal the limit as x approaches infinity of 100 divided by x raised to the x power. We're going to make use of logarithms to calculate this limit. Observe that we have a variable base and a variable exponent. Generally in that situation, we need to use logarithms to execute the limit. So let's go ahead and take the natural log of both sides. And as we have seen previously, we can reverse the outside function and the limit operator so that we have the limit as x approaches infinity of natural log of 100 divided by x raised to the x power. Then, as we've been practicing, we can take the exponent on the argument of that natural log and move it down in front as a coefficient. Now, thinking about x approaching infinity, this first little factor x approaches infinity as x approaches infinity. And here we have natural log of 100 divided by x. Well, as x approaches infinity, the argument approaches 0. And as the argument approaches 0, we know that natural log approaches negative infinity. Now, infinities can be tricky, but not in this case. If you have a factor approaching infinity times another factor approaching infinity, I'm going to ignore the negative for a minute. Well, infinity times infinity, that's just going to give me a really big number, right? So infinity times infinity is infinity. Infinity behaves weird sometimes. By the way, infinity plus infinity is infinity, but infinity minus infinity is not necessarily 0 if they're growing at different rates. Infinity times infinity is infinity, but infinity divided by infinity is not necessarily 1. We know that's an indeterminate form. So the ones that you can be confident of is when you have the product or sum of infinities. You can go ahead and make your conclusion there without any further analysis. So let's see where we are. We have the natural log of L equals the limit as x approaches. Oh, let's go ahead and evaluate the limit. We figured out this limit is infinity. And in particular, let's be careful here, negative infinity. Now, how in the world am I going to evaluate this? Well, we're going to use some unofficial notation here, e to the negative infinity. Technically, that exponent is approaching negative infinity. We can't really plug in a number that's not a number. But as that exponent approaches negative infinity, we know the value of that function is 0. Just to be sure you're with me on that one, think about the graph of e to the negative x. That is a decreasing exponential function. So as x approaches infinity, e to the negative x approaches 0. So let's backtrack and see if we can make our conclusion. We found that the limit as x approaches infinity of 100 to the x divided by x to the x is 0. The only way for this limit to be 0 would be if the denominator is increasing faster than the numerator, right? Because if the denominator of a fraction increases faster than the numerator, the value of the fraction decreases. We can say, therefore, x to the x grows faster than 100 to the x. You may have suspected that all along, and if you did, you would have been right.